Okay, today is another review day for the final in precalc, and that's coming on either Thursday or Friday, depending on which day you have my class. Basically, days 1, 3, or hours 1, 3, and 5 take it on Thursday. So I believe you guys will be taking it on Thursday. All right. So we're doing problem actually 13 from the packet, and it's describing this as a radius of a octagon, and it's not really a radius. Radiuses are for circles, but it's a line that goes out to the corner of this little wedge. Now, if I make another line going to that corner of the wedge, if this is truly a radius, then this is also like a radius. That means they're the same. And they said that it has the length of one side if the radius is 1 unit. If this is 1 and this is 1, well, here's the thing. You can't do anything because you don't have a right triangle. But you can make a right triangle by going like this. And now you have a right triangle, and that's the 90-degree angle. Okay? And this side's 1. And if that's a 90, I can also start figuring out how big this angle right here is. Because the total is 360 all the way around here, right? And then you say, okay, but there's 8 sides of this thing, so there's 8 of these wedges this big. So you take 360 and you divide it by 8. And you'd be able to tell how much this big angle is right here. So 360 divided by 360 divided by 8. 9 times 8, 7, no, that's way too big. 8 times 8 is 64, 7 times 8, 6 times 8, 5 times 8 is 40, 45? Thank you. So if this is 45 right here, then what's half of the 45? 22.5. So now we've just figured out that this triangle right here, I'm going to make it red, has a side of 1, and this little angle that's in there is 22.5. That's half of 45. So now, if you draw it separate, it might help. 22.5, and the side right there is 1. What they really want to know is how long is that side right there, that x. That sets up the trig. And from there, I hope that it's easy for you. You must say sine, cosine, or tangent. So which one has opposite and adjacent? That's tangent. Tangent of 22.5. Tangent is opposite over adjacent, x over 1. And x over 1 is the same as x. And you might say, but I don't have a calculator. Well, then the answer is tangent of 22.5. Because x over 1 is just x, so x equals tangent of 22.5. All right. That's one side of an octagon that had a radius of 1. Oh, you're right. You're right. I just figured out this distance right there, and that's only half of one of the sides. Thank you. Good catch. So the answer is not tangent of 22.5. It's twice that, right? Because if this distance right here is tangent of 22.5 degrees, then I got to do double that because I need the other side too. So 2 tangent of 22.5. Again, if you don't have a calculator, I don't think there's any other alternative, is there? All right, so now let's move down to problem 14. Secant of x equals 2. Now this is a more, this is hardcore trig. You got to start asking yourself, okay, what does secant mean? Hopefully you know what functions go together and stuff. Remember how I was having you make a separate sheet that is what you would study the night before the test? Here's one of those things I would put on my separate sheet that I would want to study the night before the test. Sine, cosine, and tangent are the big 3. But they all have a sister function that goes with them, like secant, for instance. Which one of these goes with secant? Sine, cosine, or tangent? Cosine is 1 over secant. And sine is 1 over CSC, cosecant. And tangent is 1 over what? Cotangent. All right, so how does that help? Well, you can say, I don't want to do secant. because I don't know what secant is very well. I don't know it's like opposite over adjacent and that kind of thing. So instead, you do 1 over secant, and if you do that to that side, you got to do it to this side. 1 over secant would be the flip of secant, which would be cosine, equals 1/2. See what I did there? Basically, I just put 1 over on both sides, and that ended up changing secant into cosine, and now it's a new problem, and that's a lot easier, because I know cosine. Cosine is C-A-H, you know, from SOHCAHTOA. And if I haven't written that one down already, of course, you have to know SOHCAHTOA. So the cosine is adjacent over hypotenuse, ka. And so that means if I'm going to draw my triangle, I would draw it like this, and I'd have cosine adjacent side is 1, hypotenuse side is 2, and this must be square root of 3. The one that's across from the square root of 3 is 60 degrees, so therefore I know the answer is 60. But then you should always ask yourself, is there another angle? Is there another possible answer? 60 degrees is a working angle. I mean, it works, but is there another one where cosine is positive? If all students take calc and cosine's positive there also, then there's another possible answer. If it's 60, it's also 300. Unless they gave us some reason to only take one of those. Oh, wait! Look at the directions. It says for number 14a, it says the answer has to be between 0 and pi over 2. That's from 0 to pi over 2 means I'm only allowed to have the answer that's in here. See what I mean? By that extra thing, they've eliminated the other possible answers. So I guess it can't be that. But always be thinking about that. There's often, if you are getting angles for answers, there's often an unlimited number of angles, so they have to tell you where to search between. If they said between 0 and 360, we would have given both angles, both the 300 and the 60. All right, there's another one like that on the next page, but you need to do that one for practice yourself. Instead of doing cotangent, I'd recommend putting 1 over on both sides, and then you'll be doing tangent. Okay, let's move on to a different kind of problem that would be helpful for you. Let's do number 17. Everybody look at number 17. Number 17 is talking about finding all the solutions between 0 and 2 pi. So 2 cosine x sine x, and then minus cosine x equals 0. I hope I've said this enough time that it has sunk in. If you can factor something, you should factor it. You should. If you can factor something, you should factor it. So I see there's a cosine in both of them. So I should factor out that cosine. And what do I have left? 2 sine x minus 1. Now, why is factoring good? Because now I just created this times this equals 0. And that's one of those times when I can set both of the circles equal to 0. Cosine of x has to equal 0. That's going to give me a couple answers. And 2 sine x minus 1 is equal to 0. That's going to give me a couple answers. So I'll keep going a little further on that one. 2 sine x equals 1, and then divide by 2 on both sides. Sine x equals 1/2. That's got 2 answers, I'm pretty sure. And that one's cosine. Where's cosine 0? Remember, a cosine is like x, like sine is like y, and tangent is like y over x. Cosine's the x. This is where x is 0. So if you're looking at one of these things, where is x equal to 0? Well, this is the x, and x is equal to 0 right here. So it's that spot and that spot. Those are both places where x is equal to 0. This is 0, 1. This is 0, negative 1. All right. Yes? Good question. If it doesn't say, oh wait, in the directions it said between 0 and 2 pi. That's a hint. Radians is what they want. So, all right. I think you'll find that B will factor nicely. And what do you remember about B that's different than the other kind? You got tangent. What's special about tangent? Certain things don't work on tangent. You remember that? What are the things you have to watch out for on tangent? Where does tangent fail? Well, if you give an answer that's on its asymptotes, tangent can't work. So tangent looks like this. Where is the place that tangent fails? Right here. What is that spot? pi over 2. And what's this spot over here? Negative pi over 2, but you usually see that a different way. If it's all the way around here, you wouldn't think negative pi over 2, but it is. So what's that spot also called? 3 pi over 2 is another place where tangent will fail. At pi over 2, negative pi over 2, which is kind of the same as 3 pi over 2. It's not really the same, it's just that you do it another asymptote over here at 3 pi over 2. So anyway, bottom line is, I think you'd have to watch out on B. I'm pretty sure one of the answers comes out to pi over 2, in which case tangent would crash. So you have to throw out pi over 2 because it's extraneous, because it would crash tangent. All right. Let's move on to problem D. Just look at D. It's all set up. Do you get that there's two things being multiplied on D? That is, sorry, 18D. You are correct. 18D. It's got sine x minus 3 root 3 over 2 and cosine x plus 3. Since it's equal to 0 and it's set up as a multiply, this times this, then each of them have to be set equal to 0. So you just say cosine x plus 3 equals 0, cosine x equals negative 3. Wait a minute! Cosine x equals negative 3? Would cosine ever get to negative 3? No, you can't do that, because what's the highest and lowest cosine ever goes? Remember cosine's like this? What's the highest and lowest it ever goes? 1, and what's the lowest it ever goes? Negative 1. So if you ever say cosine is going to come out to negative 3, it's not going to work. If you wanted to, they could have caught it later and said, okay, so then this is 2 sides over 1, and how can I have a side of negative 3? You can't have a side of negative 3 over 1. That, especially since adjacent over hypotenuse, the hypotenuse side is small compared to the adjacent side. That's impossible. There's like 10 reasons that's impossible. So this side of the equation, you'd have to say extraneous. Or you could say no solution, and I'm not going to be picky about that. This side, I'm pretty sure if you solve it, you're going to get a couple answers for it. Okay, now we should talk about transformations. This is the easy kind, number 19. This is not the hard kind yet, but on number 19, we're getting into like stretches and flips and moves of functions. And I'm hoping you feel like this is the easy part. Do you remember? 19a is asking you to graph 0.5, or I'm going to say 1/2 to the x. I hope you remember that things that are a fraction like this is exponential form. Y equals ab to the x. And a in this case is 1, so it's like it's not even there. If this b is ever less than 1, it's talking about decay. So generally this is decay, which looks like that red line there. Okay? Anytime you have a fraction that's less than 1, then it's decay. So if that's decay, that's kind of what it looks like. Now, how do I get it to go to this other g of x? This was f of x. G of x is a change. It started with the same thing, the 1/2 to the x, but it threw in an extra thing in front with the 3, and then it threw an extra thing at the end with a plus 4. That's a vertical stretch factor, what? 3, and then what's that? It's just simply up 4. That's all they're talking about in that whole section. It's just simple moves. All right. B, you might want to rewrite it in a more friendly way. It says 2e to the 3 minus 3x. To me, it's a lot easier if you go like this, 2e to the negative 3x plus 3. And then there's basically, the 2 is a vertical stretch. Then you got 3 things actually happening on the inside here. And normally, stuff on the inside like this that's on the inside of the function, that has opposite of normal order. So normally these guys would be first, so they're not first. This would be the first thing on the inside you'd do. And then this, of these two, they're actually tied. So I could do the horizontal shrink first if I wanted to, factor 3. And I could do the reflection, that's a left-right, which is a horizontal reflection. I if you'd rather do that first. Okay. So these are just about moves and stretches and that kind of stuff. They're pretty simple. Good question. A couple other common graphs you need to know. Y equals e to the x. That's like 2.7 to the x. That's growth because it's bigger than 1 in here. So that one's like this. And then the log graph is its inverse. Y equals ln of x means really log base e of x. And that's like this. Remember the log blown over in the wind? It's just a log base e, which is a log base 2.7. The bigger the base is, the tighter the turn it makes. So if you graphed log base 10 of x, that would be tighter. It would be more like that. If you do like log base 100 of x, it's an incredibly sharp turn. Like maybe that. That'd be like log base 100. Okay. Moving on to, let's talk about the amplitude and the period. We haven't talked about those in a while. Number 20. Do you remember, I'm going to give you this as a, instead of doing one of the problems that's in the book, 2 sine of 3x minus pi, and then plus 6. Do you remember what all these things are? That's the amplitude. You might want to take notes on this if you don't remember it automatically. This is simply shifted up or down. And do you remember this part right here? That's the B term. And when is that ever used? That B term is used in the period equals 2 pi over B formula. You remember that? You always start with a period of 2 pi if it's sine or cosine. Don't forget tangent has a period of pi. But the period is 2 pi over b is another important formula. If you're making a list of things that should probably go on in your notes, that'd be smart. All right. So if I had to answer this question, what's the amplitude in this one? I'd say the amplitude is 2. It's going to go twice as high as normal. Normally, sine only goes to 1. This one goes double that. Don't forget, too, the amplitude is not the total distance that the thing goes like back and forth. This is not the amplitude. The amplitude is half of that. The amplitude's like that. All right, I'm going to pause for a second. All right, I'm back from my little short break there. So on this one, the amplitude would have been 2, and the period would have been 2 pi over b. And what's b? B is 3. So the period on this one would have been 2 pi over 3. That would change its normal period, which would end here at 2 pi normally, to ending at 2 pi over 3. That means all these other places would have to change also, so that because this thing has been squished. All right, last thing on this kind, do you know where the phase shift is? The phase shift is in here, and the phase shift is solving that for x. So you want to get the x alone, so you divide both of them by 3. You get what I'm doing there? So I'm factoring out the 3. 3 comes out, and I'd have x minus pi over 3. So now I've got that factored. Now you can tell the phase shift. The phase shift is this part right here. So again, all I'm saying is, to get the phase shift on a problem like that, you want to factor this number out. Like I did right here. I factored out the 3, and what I had left was x minus pi over 3. Then the phase shift itself is the pi over 3. If I divided both of them by 3, watch, if I divide this by 3 and I divide that by 3, that's how I get my answer on the inside, which is x minus pi over 3. And the 3 then goes out to the front like this, see? All right, so bottom line is the phase shift is not just this number. You've got to divide both of them by 3 to get this off of there. Kind of like solving for x. Divide by 3, divide by 3. The phase shift is actually pi over 3, and it's right pi over 3. Yes? What would the period be? You want me to do the problem in the packet? Yeah. Just read the problem in the packet, make it fast. Problem number what? A, 20A. 20A. All right, so my first question is, has this been shifted at all? There is no shift on this one. So They would have to say like minus pi or minus pi over 2 or something like that. No, the period is always 2 pi unless it's been changed. And has it been changed? Yeah, 2 pi over b. What's the b? 2 pi over 5 then. That's your new period for that one. It's 2 pi over the b, and that's the b term. Okay, and then what's the amplitude? The amplitude is 6. You do not include the negative because amplitudes are a distance, and you can't have a negative distance. Thank you. Good. All right, so bottom line is the amplitude on this one would just be 6. And the period on this one would be 2 pi over b, which is 2 pi over 5. All right. I don't think it even mentions phase shift in here, so maybe we don't have to worry about that one. Okay, let's move on to number 21. We'll do some of those kind, and then I think that's enough for one day. Graph 2 periods. Aha, that's the graphing you guys were asking about. So, if I'm going to graph plane cosine, plane secant, plane sine, I'm going to tell you just all of those first, and then maybe that's enough for today to just do the graphing kind, the general graphing kind. Let me look at how many pages we have to do. Yeah, there's so many pages, we definitely need to get through that today. So, if you have notes, make a quick note of what sine looks like, what cosine looks like, and what tangent look like. And I gotta go fast because so much to learn, and this is all review. Sine looks like this. It has 4 important spots. 2 pi, pi, remember those two? Give me some of them. Pi over 2 and 3 pi over 2. Good. Okay, there's the graph of sine. And how high does it go? 1. That's because its amplitude is 1. Now that's why we say its amplitude is 1. Okay. And then cosine. Cosine starts up here, goes down and comes back up again, sort of like makes a valley. And that starts at 1, goes all the way down to -1, ends right here at 1 again, and it is at 2 pi where it finishes because its period is 2 pi. And then you got to go back and go 1, 2, 3. Those are the 4 spots. This one's halfway, it's pi. This one's pi over 2. And this one's 3 pi over 2. Is this coming back to you, I hope? Sine and cosine. Tangent is the one that's got asymptotes right here, and it looks like that. That's a pretty bad one. I'm going to try that again. There. It's kind of like the x cubed function. Just hold on, one thing at a time. So this is tangent, and this one goes from pi over 2 to negative pi over 2. Its total distance then is half of a pi plus another half a pi is 1 pi. Its period is pi. Question on that one? All right. So that's tangent. Now let's do the 3 that kind of go together with them. Sine goes with cosecant, right? Its sister function. And so cosecant rides on the back of sine. Do you remember this? And it's got asymptotes that go through here, and there. So what I just drew in red there, that's the graph of cosecant. And now I'll draw in green here the graph of cosine. That's the same deal. It's riding on the back. And like that. Asymptote lines running like this. And I've got 1 down one, a full down one, and 2 half of up ones. That means that this is a total of 1 period of cosine. Or, sorry, that was riding on the back of cosine, so that was secant. And then cotangent, I really need to draw all over again because it's totally different. It's not like riding on the back of tangent. Cotangent's graph looks like this. It's got an asymptote right here, and asymptote here, and cotangent goes the other way as tangent. It's complete reversal. And that one goes between 0 and pi. It also has a period of pi, but it does all of it from 0 to pi. Okay, so that's the graph of cotangent. All right, that's all the base graphs. Now tomorrow we'll get into taking those base graphs and doing the stretches and moves and all that kind of stuff on them. But along the lines of a sheet you could use the night before the test, I think these are worthy of that because it's really easy to get tangent and cotangent mixed up in your head, for instance. Forget which one goes between where and where. And this is the important stuff, like the graphing, that should be your easy stuff. Like if I were you, I'd lock in lots of studying time on the graphing so that you get all those questions right. You very easily could. And that makes up for other sections that are going to be just butt hard. And you're going to be like, I am going to get this whole section wrong. Well, if you make up for it by getting the whole section on graphing right, you see what I'm saying? Some of you guys could study for a week on one kind of problem that's on the test and still not get it right. So let's instead focus on all the things you are good at. And graphing has generally been one of them. Yes? Note cards are not allowed. No, you don't get a note card. It wouldn't be dumb to make one for yourself just for like practice, because I think you probably know this. The teachers that give you a note card, that what they're really doing is making you make the note card. That's where you get all the learning. Most kids never even like take much time. They might look at it once during the whole test. It's like the practice of making the note card is half the benefit. So if you want to make yourself a note card and then imagine like you're going to be able to use it, go ahead. Yes? I can come back to you. It is definitely like a test. I'm going to let you rephrase that. Do you have a question first, sir? Yes? Okay. What is the composition of the test as far as multiple choice versus free response? I think it's in the neighborhood of half and half. It's in the neighborhood of half multiple choice and half free response. Now the good part about that is most of your tests only had like one multiple choice question on them, and yet this is going to have like half of the test is multiple choice. So that's good. The bad part is there's a lot of questions and there's a lot of free response on there too. So you will need the entire time on this test. You will also need the ability to say, I'm probably not going to get this one right, and let it go. The same thing happens on the ACT test. Very few kids are able to handle the entire ACT test. You have to be able to say, okay, there's a few on here, I'm just going to let go, and that's all right. Because remember, if you can get 75% on both sections, you have an A. So if you let go of a few problems, that's all right. It'll work out. Just can't let go of lots of problems. It is scored Marzano style. So a 75% in the both sections would get you an A. All right, that's all I have for the video for today.